In this lesson, we're going to explore the basics of functions, and functions are a really, really important concept in Algebra 1 courses, but more particularly in Algebra 2 and pre-calculus courses. Functions really kind of form a foundation for algebra. Much of what we talk about relates to functions. In Algebra 1, you talked about linear functions. In this unit, we are going to briefly review linear functions and kind of set the stage for much of the work that we're going to do in this Algebra 2 course in talking about different types of functions that we encounter in mathematics. Your big idea for this lesson is the idea of what a function is, and it's important that you walk away from this lesson understanding that a pairing of items from two sets is special if each item from one set pairs with exactly one item for a second set. It's also important that you walk away understanding that a relation is simply just sets of pairs of input and output values, and that we can represent relations using a variety of different formats. So let's kind of take that essential understanding and apply a vocabulary word to it. A relation is a set of pairs of input and output values. So we put, an value like, let's say, the number 5 into something, it gets modified, and then an output is released. Kind of like we put, cookie dough in the oven and we get cookies back. When we pair those different things, I can put, bread dough in the oven and get bread back, or I can put, mozzarella sticks in the oven and get, gooey, cheesy goodness back. When we kind of combine those inputs and outputs, we get a relation. There are 4 different ways that we can represent a relation. We can use a set of ordered pairs. A couple of things to point out here. You can see ordered pairs here. So 6, 5, 4, 3, 6, 4, and 5, 8. Those ordered pairs are in parentheses. All right, if you recall from your Algebra 1 course, all right, an ordered pair is always written in parentheses. We get an x coordinate followed by a y coordinate. The other thing that you're going to see there, though, are these curly braces here at the end. That's very, very important to understand. That's what we call set notation. So those curly brackets give you a set, and inside you have those different ordered pairs, and that's what makes it a set of ordered pairs. You can also express a relation using what we call a mapping diagram. In a mapping diagram, you have these 2 bubbles, one for what we're going to call the domain, which is something we'll define in a little while, and the other for what we call a range. You can see that in the domain here we have 4 different elements, -2, 0, 4, and 5. We also have 3 elements in the range. Elements in the domain are paired with elements in the range, and we use arrows to show how those pairings happen. So for example, if we take a look here at the top, we can see here that the element of -2 from the domain is paired with the element of 1/2 from the range. The arrow points very specifically from the domain value to the range value. It's really important that when you're working with mapping diagrams, you either interpret those arrows correctly, or if you're asked to sketch a mapping diagram, that you put in those arrows correctly to pair domain to range. Another way that we can represent a relation is using a table of values, and tables can be expressed either vertically, as the one here is shown, or horizontally. What that means is that I could take my table and draw it like this. So I have x and y in different rows, and I'd have my 4 and my 6, my 8 and my 12, my 10, and my 15. It conveys the same exact information, it just looks a little bit different. The final way that we can express a relation is using a graph, and you can see a graph here. We took these distinct input and output values, so these ordered pairs, and plotted them in the coordinate plane. Graphs are kind of a sticky situation because we have a couple of different kinds of graphs, 2 in particular. The first is discrete. A discrete graph is simply composed of distinct isolated points. So if you go back to example number 4, when we looked at that graph, that was distinct points. It was an example of a discrete graph. A continuous graph, on the other hand, is one that is unbroken. So what that means is that we're going to have no jumps, breaks, or holes. Really, the big idea here is that when you draw it, you don't pick up, or you don't have to pick up your pencil, because it never stops. So this would be an example of a continuous graph. It's actually a linear graph, but you can see that there's no jumps, breaks, or holes in that graph. So we saw before in the mapping diagram example the words domain and range. Let's apply a more formal definition to those terms. A domain is the set of input values in a relation. It's really important that you understand that the input values are really the x-coordinates. So if you look at all those ordered pairs and you pick out the x-coordinates, you would be identifying the domain. The range, on the other hand, is the set of output values, which would be the y-coordinates. If we go back to my example that I used before of using the oven, the domain would be all the things that I put into the oven. The frozen mozzarella sticks, the bread dough, the cookie dough, all right, all those things, whereas the range would be the cookies or the bread or the warm, gooey, cheesy goodness that I get out of the oven. Let's look at a few examples. We want to find the domain and the range of each relation. So if we look at this first one, all right, if I want the domain, which I just label with a D, a domain is a set of input values. So I'm going to use that curly bracket, and I'm just going to pick out all of my x coordinates. So you see I'm putting tick marks above them right now. I see a 4, a 5, and a 6. Now I have 4 ordered pairs in this example, but I only have 3 items listed in my domain. That's because we only list elements once. So when you have a number that's repeated, you're only going to list it once when you're giving the domain and the range. Let's look at the range now. We want to look at these y-coordinates that I'm kind of marking here in green. I see a 3, a 4, a 5, and an 8. So 3, 4, 5, and 8. That would be the domain and the range of that relation. Looking at number 2, this one gets a little bit harder. We're still just identifying x-coordinates versus y-coordinates, but because they're points on a graph, you first kind of have to identify the ordered pairs. What I like to do is I start with the domain, and I go to the furthest left point here, all right, which would be an x-coordinate of -2, and I just work my way across the graph. And the x values that I noticed there were -2, -1, and 2. I do the same thing for the range. I start at the lowest point that I see, which would be the smallest y value. That's a -1. I also see that I have 1 and 2 as y values. You could also there take the time to just write down what all the ordered pairs were for those points. So when stating domain and range of a continuous graph, you have to use an inequality or other notation that indicates all values in the set, because what happens is there's infinitely many numbers between each of those integer values that we recognize very easily on a graph. So for example, between the 0 here and the 1 here, there's infinitely many numbers because of all the decimal values that are included. So if we wanted to list the domain for this graph, let's say, we would be focusing on the x values. So how far does the graph go from side to side? Well, as we can see, as the graph moves up, it's also moving out to both sides, and the arrows here indicate that it's going to continue to move up and out. That means that eventually every single number on that x-axis would be included in the set of values. So we call this all real numbers. All right, and that fancy R, 2 sticks with the R, that means all real numbers. If we wanted to look at the range, we'd have to figure out which y values are eventually included in the set. And so what I do is I start at my lowest point, just like we did before. My lowest value here is -1. All the y values that are included in this set are above -1. So I write these as an inequality. Y is greater than or equal to -1. Let's look at number 4, the domain. What x values are eventually included in the set? Taking a look at the arrows, it goes up and out, it goes down and out. The answer would be all real numbers. What about the range? What y values are eventually included? As it goes out, it also goes up. As it goes out, it also goes down. So again here, our range for this relation would be all real numbers. So it's important at this point that we kind of talk a little bit more about relations and maybe get a little bit more specific. We have this very specific kind of relation which is called a function, and this is a relation in which each element of the domain corresponds with exactly one element in the range. So they have what we call a one-to-one correspondence. Basically the domain values aren't shared. So let's look at a few examples and determine whether or not each of these relations is a function. And it's really important as we go through these examples that you're able to explain why it is or it isn't. So in number 5, let's take a look at this set of ordered pairs. We're going to focus in on the x values. 6, 5, 1, 7. We want to determine whether or not each of those values goes to only one range value. So the value 6 is going to -7. Is 6 going to any other y value? Because we don't have any other 6's in the set of x values, it's not. It's only going to that value of -7. The trick here is to look for repeated x values. That's how you're going to determine whether or not a domain value is being shared with multiple range values. So in this example, this is a function. All right, and we would say that each domain goes with only one range, or there are no shared x values. Each domain goes with exactly one range. How about number 6? Again, let's focus in on those x values. We're looking at these right here. Do we have any x values that are used more than once? We do, right here. What we see here is that the x value of 3 goes to a range value of 1 and a range value of -1. This is not a function. And the reason that this is not a function is that the domain value 3 is paired with 2 different range values. Take a final look at one more example, and that's number 7. Again, focusing on the domain values. This one's a little bit harder though, because when we make a mapping diagram, we don't list repeated elements. We only show 4, 5, 6. What we have to focus in on is the number of arrows that are coming off of each of those elements. The 4 only has 1 arrow coming off of it. It goes across to the 3. The 5 only has 1 arrow coming off of it. It goes down to the 8 here. But if you take a look at the 6, it has 2 different arrows coming off of it. The 6 comes over here to the 4 and over here to the 5. What that means is that the 6 is a repeated domain value, or the 6 is shared. So this is also not a function. The domain of 6 is shared with 4 and with 5. When we're determining if a relation expressed as a graph is a function, we use a different type of approach. We're still looking really for those repeated x values, but because we have a more visual representation of the relation, we can use a different test. It's called the vertical line test. How it works is that if a vertical line passes through more than one point on the graph of a relation, then the relation is not a function. So what we want to do here in these examples is not actually find the domain and range. We want to determine if these are functions. So for number 8, what we want to do is take these points and kind of test them out. If we draw a vertical line, do we ever hit more than one point? And we do right here. This vertical line right here went through both of these points. So this is not a function. And we can very simply say that it fails the vertical line test. How about number 9? Is there anywhere here that you can draw a vertical line so that it passes through the function more than once? There isn't. This is a function, and this passes the vertical line test. How about number 10? Number 10 also fails the vertical line test and is not a function. Another important feature of graphs and of relations are what we call intercepts. And intercepts are locations where a graph would cross either the x or the y-axis. So we break them down into two different categories. X-intercepts are locations where a graph would cross the x-axis, and y-intercept are locations where the graph would cross the y-axis. So in examples 11 and 12, what we're going to do is approximate the intercepts for each of these functions shown, and we're just going to simply state whether or not each is an x-intercept or a y-intercept. So let's start with the x-intercepts. What we want to do here is mark the different points where these graphs cross the x-axis, and we're going to go ahead and do both examples at once. So I've marked all those spots in red. Those are x-intercepts because they're where they cross the x-axis or the horizontal axis. So go ahead and just approximate those ordered pairs. Let's look at example number 11 first. The first one here looks like it's at 0. So we can just write 0 because we're identifying it as an x-intercept, or we could write the ordered pair 0, 0. The next one is -1. And then, positive 1. And the final one here is +3. If we look at example number 12, it looks like we cross the axis at -2 and 4. One important thing to note about x-intercepts is that with an x-intercept, the y value in the ordered pair is always 0. Let's look at y-intercepts now. So let's go back to the graph and mark now with purple, all right, where the graph is crossing the y-axis. Looking at example number 11, the y-intercept is also 0, so the x and y-intercept can match. In example number 12, the y-intercept is 2. Again, because we're clearly identifying them as y-intercepts, we can just write the values 0 or 2, or we could write them as ordered pairs. What's important to note about y-intercept is that the x value in those ordered pairs is always 0. That's part of how, if we're given an ordered pair, we would identify something as an intercept when we're not looking at a graph, because the other coordinate is 0. Another important feature of graphs that we're going to be talking about is the end behavior, and this concept can be kind of confusing. If you think about yourself just standing at the origin, as you walk away from the origin, either to the left or to the right, you want to look at where the graph is going. So are you maybe walking uphill and the graph is increasing and moving up, or you may be walking downhill and the graph is decreasing in that direction and therefore pointing down. You really just want to figure out which way the graph is pointing as you move out from the origin. So let's take a look at two examples. We want to determine the end behavior of each of these. If I look here, the graph is pointing down as we move away from the origin. All right, and here in number 13, the graph is pointing up as we move away from the origin. We always list this in left-right order. So the end behavior here would be down and then up. So left, right, and it's down and up. What about number 14? What direction is the graph pointing to the left-hand side? It's pointing down. How about on the right-hand side? Also pointing down. So the end behavior here would be down, down. We also need to talk about the idea of minima and maxima, and it's important that we break this into two separate categories: relative minima and maxima and absolute minima and maxima. Relative minima and maxima, there can be multiple instances of this type of point in a particular graph. Really what's happening there is that the value of a function, or it's the value at which a function is turning from either from up to down or from down to up. It's really what we call a turning point of a graph. If you think about like a roller coaster or something, it's like the top of a hill or the bottom of a valley. If you think about, a graph that's a V, absolute value graphs, which you've seen before, it's that turning point down at the bottom of the graph. An absolute minima or maxima, on the other hand, is the strictly highest and or lowest point overall for the graph. So in examples 15 and 16, what we're going to do here is not only approximate the minima and maxima for each function, but we're going to state whether or not the point is a relative or absolute minima or maxima to kind of clarify which one is which. So let's look at number 15. What we want to do is identify all turning points, so like here and here, and we're going to start there. So what are our ordered pairs? Well, this appears to be at approximately 1/2, -1/2. It's not the absolute lowest though, because if we look here along this line, there's points over here that are even lower. So this is going to be considered a relative minima, or relative min. How about this one here? Looks like we're at about 2.1, 2.1. And again, there's other points at other parts of the graph that are higher. So this is what we would call a relative max. Let's look at number 16. We're trying to identify all turning points. We only have the one right here. The ordered pair here would be 1, 3. Are there any points that are higher than this point? There aren't. This is an absolute maximum. All right, it's the very highest point on the graph of that function. Final concept that we need to talk about are intervals where the function or the graph might be increasing, decreasing, or constant. A graph is increasing when it rises from left to right. It's decreasing when it falls from left to right, and it's constant when it's perfectly horizontal, so when there's no change in how the graph rises or falls. When we're determining these intervals, it's really important that you focus on the x values of each ordered pair. Just like we said before with domain and range for continuous graphs, it's important to note here that we can state intervals using multiple methods: inequalities, interval notation, or set notation. We are going to focus in this course on using interval notation. Let's take a look at a few examples. We want to determine where each graph is increasing, decreasing, or constant. So let's take a look at 17 and 18. What I like to do here is I like to just have the increasing, decreasing, and constant spaces set up, and I like to mark my turning points because that's where it's going to change from increasing to constant to decreasing, and any mix of those. And I also like to put on here my ordered pairs. Now this is the same graph as we just saw above. So let's fill in the ordered pairs that we had before. All right, 0.5, -0.5, and 2.1, 2.1. What I do now is I just read the graph from left to right. So let's start here. What is the graph doing here? Is it rising or falling from left to right? In this case, it's falling, which means that that's a spot where the graph is decreasing. This x-coordinate up here, because the graph keeps going, is considered negative infinity. So that means that this graph is decreasing from negative infinity, all right, because we don't see that it ever changes or turns again, all the way to 0.5, all right, or to 1/2. What happens next? What happens when it reaches this turning point? The graph then begins increasing, and the graph increases from 1/2 all the way to 2.1. And then the graph begins to fall again. So then it falls from 2.1, and then this would be positive infinity out here. There are no sections where the graph is horizontal, and therefore there are no sections when this graph is constant. The ideas of increasing, decreasing, and constant can be really confusing. It's really, really important that you label those turning points and that you read the graph from left to right. Are we falling and going down that big hill on the roller coaster? Are we maybe climbing? Or are we kind of in that boarding area where we might be getting on and off the ride? Let's look at number 18. And again, we're going to label these turning points. So this looks like it's at -2, -3. And this looks like it's at 1, -3. So increasing, decreasing, constant. And let's also label here our negative infinity and our positive infinity because the graph does keep going. What's happening here on the left-hand side? We are decreasing, and we would decrease from negative infinity to -2. At -2, what happens to the graph? It looks like it becomes perfectly horizontal. So in this case, this graph is constant from -2 to +1. And then the graph kind of takes off, and it's going to be increasing from 1 to positive infinity. Interval notation is really interesting because for the most part, it actually looks like ordered pairs. There are going to be some cases that we may learn about in the future where the type of end cap that you use is important. In this case, we used all smooth curves because of the fact that the points aren't really necessarily included. Like, it's kind of a transition area. So that's why we just use regular parentheses. There are times with interval notation where you're going to use squared off brackets. It's a matter of whether or not a point is included or not, and that's something that we're going to talk about a little bit further, possibly later on in the course. So this has been the lecture on function basics. I would encourage you to go back and rewatch any parts that might be unclear, but also to kind of review your notes at this point and determine whether or not there are any things that you really don't understand. Those are the things that you want to ask about when we get to class during our next meeting.